Okay, so thank you very much for the introduction, Antonin, and to the organizers for the kind invitation. Yeah, it's actually my first time at the ESI and the first time in Vienna for business reason. I've been here for tourism, and it's a very beautiful city, and this is a very beautiful institute. Okay, so I'm going to take from and also a special thank to Tim for introducing Brakke flow, mean curvature flows, and I'm going to talk about this regularity theorem. So I'm going to do some regularity theorem for Brakke flow solutions near triple junctions, and I'm going to explain why we are interested in that. And what I'm talking about today is a joint work with Yoshi Tonegawa, who is there, and is on the archive. Okay. So, Brakke flows, Tim has already introduced them. Let's say that we want, maybe the best way to introduce why we want to study Brakke flows is from the words of Brakke himself. So, from his PhD thesis, he wrote the following. He wrote, a physical system which moves by mean curvature is the motion of grain boundaries in a near impure metal. So, he was interested in a sort of let's say physical problem. When you have a metal, you heat it up and then you let it cool down. And when this happens, you see at the level of the metal this grain structure, and the energy of the grains is sort of proportional to the area of the interfaces between the grains, and therefore, when cooling down, you assume that these guys are going to move by mean curvature. And then because of this situation, because this is the sort of surfaces that he was interested into, then he posed the point that you can't work with smooth manifolds in general. And so he wrote, the question arises, what do we mean by a surface? We do not want to restrict ourselves to manifolds. Firstly, because a manifold may evolve singularities, and this is exactly what Tim showed us with the dumbbell. And secondly, because systems like grain boundaries is most interesting when they are not manifolds. And for surfaces, we shall take a certain class of Radon measures known as varifolds, which and this is where these multiplicities that Tim was talking about come from. So the idea, and this has been already introduced, is that the idea of Brakke is that the information that the velocity of surfaces, what the velocity of surfaces is encoded into a formula for this derivative, right? So instead of writing down a PDE for the velocity of surfaces, you can do the following. You can take your imagine even smooth family of surfaces that are evolving in time, and then integrate test functions over it, and then take the rate of change of these integrals, right? So the derivative of these integrals. And if you do this for smooth flows, right, that are flowing with velocity v, then this is the identity that you take. This is just an easy calculation, right? You can also take test function which depend on time, and then you're going to get this extra blue term in here, so partial derivative of phi with respect to time. So this is true for every let's say, smooth flow of surfaces which evolve with velocity v, right? And therefore, of course, you can integrate that between two times, and you get this identity for smooth flows. And if you want, and if your solution is a mean curvature flow, then you can just replace the velocity with h inside that formula, right? And then you get this identity. Now, if you look at this identity from the point of view of smooth surfaces, then you realize that everything that is written in here can be written in the sense of varifold, right? So, I will not enter too much into varifold geometry. Most of you know what I'm talking about. So instead, I'm going to replace the measure on the surface with, mass measure of varifolds, and this encodes multiplicities inside. And this is instead the distribution on mean curvature of mean curvature vector of the varifold, and then you may write this identity. Now, as you saw in Tim's talk, Brakke didn't write this identity. Brakke is not an identity, but is in fact an inequality. And the reason for this is that the reason why you want an inequality but not the identity is that you want to make sure that the class of objects that you define is large enough to contain all possible limits of smooth solutions. And the thing is that if you write, I mean, if you have a sequence now of varifolds which are actually smooth manifolds, so imagine that you have VT k, right, for an index k, and they are converging somewhere, right? You can see that on this right-hand side, you will see the L2 norm of the mean curvature, right, in space-time. And with respect to weak convergence, the L2 norm of the mean curvature is just semi-continuous. It's just lower semi-continuous. It's not continuous. So even if you have a sequence of smooth solutions which satisfies the identity, then in the limit you cannot expect the identity, right? You should only expect the inequality, and therefore you should only restrict to test functions which have a sign. This is what we refer to as Brakke's inequality, and now there's a caveat, and this is what Tim said already, that Brakke's inequality allows for sudden vanishing, right? You can take your favorite Brakke flow, and then you can decide to take, you can take a favorite time in the future, which is this tau here, and then you can decide to construct a new flow, which is identical to the old flow until time tau, and then is zero afterwards, right? You just make everything disappear at once, and then you will see that this satisfies Brakke's inequality. So, of course, I mean, this is highly unphysical, and therefore, in practice, one never really wants to consider Brakke's inequality alone, but rather prove the existence of Brakke solutions with additional properties so that this behavior is ruled out entirely, and this was essentially the topic of Tim's talk, right? I mean, you don't want only Brakke, maybe you want Brakke plus distributional, right? Something like this. So what Tim called variational solutions. But what is remarkable, and this is what the topic of this talk instead, is that Brakke's inequality alone is sufficient to prove some regularity. As long as you, say, assume that you have a flow that survives until a certain time, right? Because, and so let's enter a little bit this topic of regularity. First of all, let me tell you what are the assumptions of this talk. I mean, where are we in which setting we are working? So we are working in a setting where we have a flow. So time is going to be in an interval like -4, 0 of varifolds k-dimensional. So dimension is k. It's maybe not written anywhere, but dimension is k. It's going to be k. And these varifolds live in the ball B2 of Rn. So dimension is k, and dimension of the ambient is n. So this is general dimension and codimension, whatever I'm going to say today. I'm going to assume the following, that for almost every t, these varifolds are integral. So that means that they are, a rectifiable set. So let's say countable union of subsets of C1 manifolds up to a set of measure 0, each of which is weighted with some integer multiplicity, okay? And they satisfy this local uniform bound of mass in time. Now, this is not really needed to assume it for a Brakke flow, but you will see that I'm not going to consider only Brakke flow. I'm going to consider even Brakke flows with some possible forcing that is coming up in a moment. Then I have to assume, of course, that the generalized mean curvature, I mean, the distributional mean curvature vector exists and is L2 in space-time to make sense of the energy that Tim wrote. That Brakke's inequality is satisfied, and in fact, I will assume that Brakke's, you remember, right, that in general, for the general calculation that I did in a smooth setting, here there was V, right? There was the general velocity of the flow. So I'm going to assume that not necessarily this inequality is satisfied, but more generally an inequality of this form, where here I have H plus possibly some extra forcing term, which is an ambient vector field that is given to me. And that satisfies this regularity, these integrability assumptions, right? So I want this vector field to be sufficiently integrable with respect to the mass measures of varifolds. It's LQ in time, LP in space, and I want this quantity to be positive. Okay. Now, I'm talking about regularity. So, I mean, if you know what Allard's theorem is telling you, and you forget, and you think of this in the stationary setting, and you forget about time, so you just kill this term. This condition is that P, so the integrability in space, is larger than the dimension of the varifold. This is exactly the condition under which you can prove Euler's theorem for varifolds with a mean curvature in LP. So this is my assumption. And then I'm going also to assume always that this flow is a left continuous function. This as Radon measures a left continuous function of time. This you can always do because Brakke's inequality implies that when you test this with a test function, this Vt of a test function is an almost monotone function of time. Then because it is an almost monotone function of time, then you will see that this has essentially only countably many discontinuities, right? So this is a set of measure zero of discontinuities, and you can just decide what you want to do at those points, and we decide to just fill it from the left, okay? So that you can always do, and it doesn't change anything else. So these are the assumptions which I will label A1 to A5. And it's important, so at some point in this talk, A6 will appear and it will have a certain importance. Okay, these are, but you agree with me that these are essentially standards. I'm not asking essentially anything besides the fact that it's a Brakke flow. Okay, how do you talk about regularity? Typically, when you want to talk about regularity of solutions to geometric variational problems, then what you do, right, is look at a point and you may want to blow up. So hopefully you have a monotonicity, you have a geometric variational problem. Hopefully you have a monotonicity formula, and monotonicity formula, right, will come in the talk after mine. So Alessandra will tell us a lot about monotonicity formulas, I imagine. But in this case, the monotonicity formula that you have for mean curvature flow is this monotonicity formula Huisken, that was then extended, that was proved by Huisken in the context of smooth mean curvature flow, and then extended by Ilmanen to the context of Brakke flow. And it works like this, that if you pick any point space-time, and then you define the backwards k-dimensional heat kernel, which is this guy, is rho, I'm gonna call it rho. And then Huisken monotonicity formula tells you that the integral, that if V is a Brakke flow, then the integral of rho is monotone, right? So it's actually monotone decreasing. And this is the right-hand side. You can conclude, I mean, for smooth solutions, you have equality here, of course. I mean, for Brakke solution, you have just the inequality. In particular, it tells you that the limit of this quantity exists and is called the Gaussian density. Now, as usual, when you have a monotonicity formula, you have existence of densities, and then you have the possibility to blow up, right? So that's what you do. The blow up is a parabolic blow up. Fix a point, take your varifolds, and then the blow up parameter is rho in here, and you're just gonna essentially translate in time by t naught, in space by x naught, and then you're gonna dilate time by rho squared and space by rho in such a way that you're performing a parabolic scaling. This is the scaling under which Brakke's inequality is invariant, right? And then you prove that as a consequence of monotonicity formula that for every sequence rho k that goes to zero, there is a subsequence so that the corresponding sequence of Brakke flows converges to a limit Brakke flow. And this limit Brakke flow, which I call here v hat of the rescale time s, is self-similar, right? Because in the limit, this guy is going to satisfy this as an identity with this guy equal to zero, right? So in particular, it's going to satisfy this equation, which is typically called the Schrinker's equation. For all negative s. All negative s because, I mean, you only see what happens backwards in time because this is what your backwards heat kernel allows you to do, right? And then you can do a little bit of stratification as usual, which is, it's general theme of looking at points, looking at possible tangent cones of solutions. This is already, Davide talked about it, for example. You look at, possible tangent cones, because by the way, of course, I mean, here tangent flows are non-unique in general. So if you change sequence, then you may converge to something else, right? To two different limits. You look at points, you look at all the possible tangent flows of your original nonlinear flow at that point. You and you classify points based on how many symmetries, right, the possible tangent flows have. And in this case, symmetries will be symmetries in space and in time, if you want, right? And the stratification theorem, which in the setting of mean curvature flow was developed by Brian White, it tells you that, in fact, most points, from the point of view of parabolic Hausdorff measure, have a tangent flow which is a static. Static means independent of the scale time S, plane of the same dimension as your surfaces, right? In particular, all regular points, so all points where there is a neighborhood where the solution is in fact a smooth mean curvature flow, have these tangent flows, right? So if you have a smooth solution in a neighborhood and you perform the parabolic blow-up, then what you're going to find is a plane, which is the tangent plane at that point, and that guy static in time, right? That doesn't move in time. In fact, if you have unit density flows, the converse is true. Namely, you can prove, and this is a regularity theorem, it's typically known as Brakke's local regularity theorem. And for this, you can see, you can check these papers. So it's a paper by Kasai and Tonegawa, 2014, Tonegawa and myself from 2024, and an alternative proof that was given by Guido De Filippis, Carlo Galparetto, and Felix. It tells you basically that, if you have a Brakke flow, a flow as above, which in a regional space-time is sufficiently close in a weak sense and in measure to a k-plane static counted, let's say, counted with multiplicity 1, and say it survives until the end time is t equals 0 here, then the flow must be a C1 zeta graph over the plane. Okay. So this is zeta. Zeta was the number, you remember, 1 minus k over p minus 2 over q. So this is an epsilon-regularity theorem. Essentially, it tells you that as soon as your flow, as above, happens in some region in space-time to be weakly close only in L2 and in measure to a plane, to a static plane, and that plane is counted with multiplicity 1, that's very important, then, in fact, in a smaller space-time region, the flow has to be a C1 alpha graph. And in fact, of course, if u is equal to z, if the forcing is equal to 0, then this is going to be a smooth C infinity solution to the mean curvature flow. Now, once this is understood, the next relevant question for unit density flows, in a way, is to ask yourself the question, okay, how does the flow look like near a singularity, right? So suppose that at a point I blow up and I don't find this nice plane to which I can apply this regularity theorem, then what do I do? Then what do I know about the solution near that point? And then, in general, the answer that I give you right now is nothing. Nothing, right? In general, but you can try to go stratum by stratum, right? You can start saying, okay, then suppose that I'm losing planes, so I'm losing one symmetry in space. Let's say that I go to the next stratum, so I reduce my symmetries, and I suppose that so the next stratum, the most singular points by stratification are the ones which have a tangent flow which is static in time, right? And there's an invariant space of translation of dimension 1 less with respect to the dimension of the manifold. So not a plane, but not a plane Rk, but Rk minus 1 times a one-dimensional stationary cone. And the simplest example of one-dimensional stationary cone then would be this guy. A triple junction, like 3 half lines that are meeting at the origin, forming angles of 120 degrees with one another. Okay, so that's the general thing. Okay, and also that's why we are interested in triple junctions. And triple junctions are also interesting because, in fact, they are, sort of the model singularity, or one of the model singularities for what happens in nature, right? So these is the singularities that Plateau predicted for subfilms, and you imagine that this is connected to what subfilms look like. Anyhow, so that's the theorem. that I want to discuss today. This is, as I say, an informal version of the theorem. It says the following. So suppose that you have a flow as before, so a flow in B2, k-dimensional, which satisfies those standard assumptions, which I call A1 and A5. And assume furthermore two things. Well, first of all, I want to say that my flow is close to a triple junction, right? So, and this is 1. So in the parabolic cylinder, this one, V is weakly close in L2 and in measure to a static unit density cone consisting of 3 k-dimensional half planes meeting along a linear subspace and forming 120 degrees with one another. This is the standard assumption. And then I'm going to put another assumption, which is a red assumption, that V satisfies the assumption A6 to be defined in a moment. A6 is coming. Then what happens? That in a smaller parabolic region, so for time in between -1 and 0 and in B1, your flow is C1 zeta deformation of the cone. Okay? So this is the theorem. Namely, what is your flow? It consists of 3 k-dimensional surfaces with boundary, right? They are moving in time, and they are moving by force mean curvature in the interior. They are C1 zeta in the interior, C1 zeta up to the boundary, and they meet along a common k-1 dimensional submanifold of class C1 zeta, forming angles of 120 degrees with one another. So if you have a situation where locally, in a region, you are weakly close in measure and in L2 to the triple junction, then you know exactly how your nonlinear solution looks like. I mean, it's the only singularities that you have are along this sort of common boundary, which is a diffeomorphic image of this k-1 dimensional spine of the cone. And otherwise, I mean, you have these 3 smooth surfaces that are attaching to it. Of course, so the situation is this. This is the cone that you're looking at, and suppose that 0 is a point of the support of the varifold. Then, if I tell you that in this region the flow is L2 and measure theoretically close to this cone, and I ask you, okay, can you draw what the flow looks like? Then the answer is yes. I mean, the flow must look like this, more or less. Okay? Something like this. Okay, so first, let me now enter more the detail of what those two assumptions, 1 and 2, mean. First of all, what do I mean? Weakly close in L2 and weakly close in measure. I mean the following. So from now on, I will use this capital X letter to denote points in space because I have a splitting, right? So I have my cone, right? My cone is say this one, right? A triple junction, right? And points in space will be denoted by capital X, and capital X has 2 coordinates. One is the coordinate along the spine, and this I'm gonna call Y, right? And then X is the coordinate orthogonal. So X is little x, and then Y. And let's say that we are in codimension 1. So the spine, this is a k-dimensional cone, so the spine is k-1 dimensional, and X is then in R2, right? All the rest, I mean, this guy is the plane, right? Is the plane which hosts, you know, the triple junction, the skeleton of the cone. Okay, so I will say that that a flow is epsilon close, is in an epsilon neighborhood of the cone if this happens. So L2 close means that if I compute the L2 norm, the L2 distance from the cone in space-time, then it is smaller than epsilon squared. And also I want my forcing term to be smaller than epsilon in norm, and the norm is LP-LQ. In measure means that at the beginning of my evolution in the ball, I have, let's say, I have less than the area that a triple junction with multiplicity 2 would have. Okay, so I want to make sure that I have multiplicity 1 triple junction, and this is this assumption here. Actually, I think you can do better than this. It's an older version. less than, say less than the area that 2 times this would do, right? And then the third assumption is that the flow has somehow survived at time 0. So time goes from -4 to 0. So this is the end time of the evolution, and I'm assuming that. So the notation here is that this is the point V1, this is the point V2, this is the point V3, and my assumption is that around this point, and no, sorry, this is V3, and around this point, at the end time, there is some mass of the flow. Okay, so I'm assuming that the flow hasn't disappeared before. That is an assumption that I have to make exactly because Brakke's inequality alone doesn't guarantee me that this doesn't happen. A branch doesn't disappear just because somebody makes it disappear. Now, this condition of being in a neighborhood is satisfied by tangent flows, right? So this is a remark that tells you that if you give me any epsilon, and I know that at some point a tangent flow to the flow is the cone C, then at some scale the blow-ups will enter this tubular neighborhood. And also the fact that because I have this assumption, because I know that at the beginning of the evolution I have less mass than 2 times 2 triple junctions, then this information will propagate along the flow because the mass is decreasing along the flow, and therefore I will always be less than 2 times less than the mass of 2 triple junctions, and in fact you can prove that in a smaller parabolic cylinder the flow is actually multiplicity-one. So it's a flow of varifolds which almost everywhere have multiplicity equal to 1. Okay. Integral varifolds with multiplicity equal to 1 almost everywhere. So this is what I mean to be close to C. And now I have to tell you what I mean to satisfy A6, right? And then I will try to explain why we need it. This assumption A6. Assumption A6 asks the following. Now, take your flow. I'm assuming that there is a constant C1 with the following significance. That every time that you take a parabolic region inside your domain, so suppose that these points are the origin, and suppose that after a rotation you are in the neighborhood of the cone with multiplicity-one, okay? Then you know that for almost every time the support of the varifold is a multiplicity-one rectifiable set. And you can take slices of this rectifiable set. Slices with respect to, with planes that are orthogonal to the spine, okay? So what I'm asking is the following. For every time, and for every time, and for every point y on the spine, take the slice of the flow at that time and at that point, call it mty, and call k for each of these guys, calculate the distance. So the picture is the following. There is a picture coming after, but the picture is the following. So you have your cone, right? Then you have your solution somewhere, right? Look at, so this is what happens when you slice, right? You have a 2-dimensional picture, right? And then you have your cone and you have your solution somewhere. Look at what happens in an annulus, right? Call k the maximal distance of the solution from the cone in L infinity in this annulus. And then I ask that then in the whole ball, the slice of the flow has at least the same length as the triple junction up to an error which is possibly quadratic in this case. And that the slice also has second moment. This little x, for a capital X, this little x is the distance from the spine. So this is effectively the second moment with respect to the axis of the cone, right? So I want that it has at least the same second moment as the cone up to an error which is quadratic in this case. Okay? So I'm assuming these two things. Now, the picture of what happens when, for example, I mean, how a flow looks like when this assumption fails. Okay? For example, when A fails. This is a picture of what a flow would look like or what a slice would look like in your plane when the first condition fails. Here you have your slice, so you have your two-dimensional plane, you have your cone, and then you have your solution, your flow, which is this blue guy, right? And what happens to this blue guy, I mean, we will see in a moment that you will know, just from Brakke's regularity theorem, right? Imagine this. You know that the flow is locally close to the triple junction. In particular, if you go far away from the spine of the cone, the flow is close in L2 to each of the planes of the triple junction. So Brakke's regularity theorem will tell you that in that region, far away from the spine, you are a graph, right? You are a nice graph onto the plane. That's why I drew this blue solution. I know that this blue solution must be like this, all right? A nice graph over these three things. I also know something else, in fact. I also know that if you enter the red region, somewhere you must have triple junction point. And this is because essentially triple junction singularities cannot be perturbed that way, in a sense. So I know that there is a point where I have a triple junction singularity, but this is in general not enough to guarantee that this bad situation doesn't happen, right? That the flow is a graph here, a graph here, a graph here, enters, forms a triple junction singularity here, but then it does a little curl, like a little circle, and then it goes back. And this object has clearly much less length than the length of the triple junction. Okay? So you remember that the assumption that I'm making is that up to an error which is quadratic in the L infinity norm here, in the annulus, so outside of this red region a little bit, the slice of the flow must have at least the same length and second moment as the cone. Okay. So my assumption A6 is an assumption which tells me just don't look at these guys. Don't look at situations where this can happen. Okay, and now you should have a question, right? It's like, okay, who tells you that this happens ever, right? So who tells you that you have solutions where this happens? And in fact, we do have plenty of solutions which are easily seen to satisfy this assumption A6. Okay, first of all, let me tell you what the theorem is in less informal, more formal way. Is an epsilon-regularity theorem that tells you there is an epsilon universal with this property that if you have a flow in B2 which satisfies A1 up to A6 and is epsilon close to the cone for epsilon less than epsilon 0, then in a smaller parabolic region, it's a C1 zeta deformation of C, where zeta is always that guy. Namely, for every T, the varifold is multiplicity-one and it consists of the union of three graphs of functions defined of the branches, which are C1 zeta up to the boundary. They meet along this common boundary and form 120 degrees with one another. With these estimates, so the C1 zeta norm is controlled by, you remember mu was the L2 norm in space-time of the solution, and this U was the norm of the forcing term. Okay. Now, validity of A6 is what I was telling you. There are, in fact, plenty of solutions which satisfy this A6, and it's easy to prove it. You can pretty easily prove that that assumption A6 is satisfied as soon as you have, for example, in codimension 1, as soon as you have flows which have cluster-like structure, namely flows that are boundaries of sets of finite perimeter, okay? These are typically called multi-phase flows, and a pretty robust existence theory was developed by Kim and Tonegawa, and then afterwards works by Tonegawa and myself. This is what in a way Tim referred to as canonical Brakke flows. So the fact that you have you have partitions of space, so and your flow is the boundaries of sets, and you can look at the characteristic functions of the bulks, right, as Tim was doing. So when you have this structure, this underlying structure, then you can prove A6. You can prove, what do I mean when I say that you can prove A6? You can prove that if you have a flow with this extra structure which satisfies A1 up to A5, then it also satisfies A6, okay? And also in higher codimension, general codimension, you can prove it that for Brakke flows which have an underlying structure of cycles modulo 3, such as, for example, those that you can obtain by performing the elliptic regularization method of Ilmanen using currents modulo 3, as is done in a paper by Brian White and Felix, and I will come back to this paper in a moment. Let me tell you very, very quickly why, for example, you can prove A6 in the case of clusters, right? I mean, it's pretty easy. You know that outside, for what I told you before, you know that for outside you have these three graphs, right? So you know that your blue solution is these three curves that are nice, you know, slices of C1 alpha graphs that you know, and is Brakke telling you. And therefore, I mean, if you also know that you have a cluster-like structure, then outside you also have the sets of finite perimeter, and you have exactly three sets of finite perimeter, which these curves are bounding. And let me call them E1, E2, E3. And then you enter the red region, and you have no idea what is happening in the red region, right? You may have a plethora of other sets. You may have E4, E5, some little domains that are forming in that red region. You have no idea a priori. But what you know is that the length of the solution is at least the length of the perimeter minimizing cluster that that you have with this boundary datum. And that guy has the same length as the triple junction, has exactly the length of the triple junction. So you do comparison with the perimeter minimizing cluster, and you get that assumption, okay, easily. For mod 3 currents, you do some similar thing using homological arguments. I mean, you see here, I mean, when you create something like this, then you are creating boundary modulo 3. So, I mean, you can't you can do this sort of behaviors if you are assuming that you are a cycle modulo 3. Okay. So a couple of corollaries. You know, two things. From the epsilon-regularity theorem, you have uniqueness of tangent flows. In particular, I mean, you are going to know that if you have a flow which has cluster-like structure or mod 3 cycle structure, which is close to a cone below the threshold of the regularity theorem, and you know that somewhere you have a point which has sufficiently high density to support a triple junction, that point is a triple junction, right? So therefore, the tangent flow at this point is unique, is a static triple junction, and you will know that blow-ups converge to it with a rate that is a power law of the blow-up parameter rho. Okay, so this is a consequence of the theorem before. And you can also deduce a structure theorem for Brakke flows with cluster-like structure or mod 3 cycle structure in under an assumption. Namely, the assumption is that so suppose that you have a flow like this, which has no static tangent flows of the form one-dimensional cone times RK minus 1 for a cone with density bigger than or equal to 2. You know, I mean, imagine, look at these stationary cones and imagine what they are, right? So they may be, inside here there are planes, right? When C0 is a line, these guys are planes. There are, of course, the triple junctions inside, and then there are multiple junctions, right? C0 may be a union of 4 half lines, or it may be the union of more half lines, right? You can do whatever you want. So assume that you know for some reason that in a region of space-time, right? That in a region of space-time, you don't have anything with density at the origin bigger than 2. So what is the possible density at the origin? So these cones are only union of half lines. What are the possible density at the origins? It may only be 1, right? And in that case, you would know that this guy is a plane, and therefore in a neighborhood with multiplicity 1, in a neighborhood you will be regular, right, by Brakke. Or 3/2, and if it's 3/2, then it's a triple junction with multiplicity 1, and therefore you are regular by our theorem, right? In fact, under this assumption, in particular, this assumption is excluding planes with multiplicity 2, right? So if I know that all these guys are not there, including higher multiplicity planes, which are horrible, right? You may have branching there, and we are trying very hard to understand what happens with branching in mean curvature flow. Then you can prove that the singularities of the flow, namely these are the points in space-time which have the composition, for which there is no neighborhood where the solution is a smooth mean curvature flow, can be decomposed in this way, where the regular part is a k-dimensional submanifold of class C1 zeta, and the singular part has parabolic house of dimension at most k. So, in particular, this is telling you that for almost every time, the singularities are, so you have a k-dimensional, for almost every time, under this assumption, your flow is done like this, that it's a k-dimensional flow, which has singularities of top stratum singularities of dimension k minus 1, 1 less, which are regular, which are a manifold of class C1 zeta, and all the rest has lower house of dimension, Euclidean house of dimension now, for every time, for almost every time, okay? All right, so I essentially have no time to tell you anything about the proof, but there are two important things that I need to tell you. First, this theorem didn't come out of nowhere. Something else was done before, and the most important papers in this direction were a paper by Yoshito Negawa and Neshan Vikramasekara, who proved this theorem in 2016 for the dimension 1 in the plane. So one-dimensional in the plane, okay? And then there is this beautiful paper by Brian and Felix in 2020, who prove a regularity and compactness theorem for some special classes of Brakke flows in arbitrary dimension and codimension, which they call smooth flows with triple edges. And they also prove regularity of flows of currents modulo 3 when they are obtained by the elliptic regularization scheme. So, in a way, for mod 3 currents which are obtained by the elliptic regularization scheme, the regularity theorem was already known thanks to the result by Brian and Felix, by Felix and Brian. And in my mind, then I had the B and F, but it's Felix and Brian. Brian, Felix. But what I'm telling you, what we are telling you with this theorem, right, is that in fact the fact that you obtain them through the elliptic regularization scheme is not necessary, right? That the regularity at triple junction is in fact a property of Brakke's inequality, together with something else. And then more influential for us is this paper, which did essentially what we proved in the elliptic setting, right? So in the stationary case, in the case of stationary varifold of multiplicity 1. So this is a beautiful paper. It's, you know, if you're interested in regularity theory, and for whoever younger students that are interested in regularity theory, I think should read this paper because it's beautiful. And Leon Simon introduces the idea that the ideas that we use, so what is called the blow-up method, and that's what we use in our proof. Needless to say that in order to adapt the blow-up method from the elliptic case to the parabolic case, I mean, that's difficult essentially because you know, as usual in this business, when you have stationary varifolds, whatever holds true, okay, That's a bold statement, but whatever holds true in terms of regularity for stationary varifolds holds for varifolds with mean curvature that is sufficiently integrable, right? LP, P bigger than dimension. And now in mean curvature flow, the mean curvature is L2. That's what the energy is telling you, right? And this is what helped Yoshi and Nishan here, because they were dealing with one-dimensional objects and 2 is bigger than 1. But if you want to deal with higher dimensional objects, then you're lost, okay? And so I think their contribution was to show that under that assumption and that assumption ACX alone, which you can prove in a good chunk of situations, then you can actually perform the blow-up method of Simon nonetheless, even though you only have in L2 integrability of mean curvature. And there's the whole proof afterwards, but I think I'll stop here and thank you very much for your attention.